Hello and welcome to the presentation of the article From Level 4 to 5, Getting Rid of the Safety Driver with Diagnostics in Autonomous Driving. My name is Stefan Orff and I'm with FZI Research Center for Information Technology. Let us have a quick look at the agenda. First of all, we will provide an introduction and give some insights to the autonomous driving ecosystem. Next, we will present challenges of modern-day autonomous driving. The main part comes in section 3, where we provide a concept for diagnostics in autonomous driving. And finally, we will have a conclusion and an outlook. So let's start with the introduction, where we give some examples and characterize modern-day autonomous driving. Imagine the detection system in an autonomous vehicle recognizes road signs that do not match to the rest of the environment. When sitting in an autonomous shuttle bus, it would be beneficial for the steward or the passengers to be warned of an unexpected countermeasure the autonomous system might execute in the following, like an emergency stop or moving to the roadside. In another example, operators of large fleet of autonomous vehicles surely want to minimize downtime. In case of a failure, a remote operator could assist and support a non-expert steward in eliminating the error. Even in the case where no failure is present, operators are interested in monitoring and controlling their fleet. Both examples show that insights on the healthiness of the underlying autonomous systems are crucial. Modern-day autonomous driving comes with several use cases. For example, there is individual door-to-door transportation with no predefined bus stops, on-demand public transportation where there are no timetables, or parcel delivery vehicles with no safety driver at all, which is also an example for Level 5 autonomous driving according to the SAE levels. According to law and regulations, vehicles that participate in public road traffic usually need an admission. For mass production cars, this is done during the development of the vehicle itself and requires a lot of effort. But vehicle manufacturers can build up on earlier admissions and standardized procedures. For autonomous vehicles, such an admission process is not yet established. Currently, in Germany, autonomous vehicles which participate in public road traffic need an exemption to the general admission rules. These may be granted by the local authority and is based on expert opinion and safety analysis, which requires an inspection of the vehicle's hardware and software regarding the special adaptations. In Germany, these may be done by the so-called TÜV. Autonomous driving software usually follows a component-based design approach, because there are clear distinguishable tasks like localization, path planning, object detection, and so on. The benefits of component-based software designs are clear. Each part is encapsulated behind defined interfaces, which makes development of the whole system faster as components may be built by separate teams. Also, the components are not restricted to a single platform. Different computers may host different components, which communicate via, for example, via a network. Another advantage is the interchangeability of components during runtime. Components may be switched off if a malfunction occurs and exchanged by more robust components that deliver the same functionality. An example for a component-based software framework which has a wide application in autonomous vehicles and robotics is ROS, the Robot Operating System. With these preliminaries, we come to the challenges of modern-day autonomous driving. In modern-day autonomous driving, several actors are involved during development all the way to operation. First, of course, there are the developers. As there are a wide range of functional tasks, many different experts are involved. These experts may also be from multiple companies or manufacturers. Although component-based design makes development with multiple teams easier, all have to agree on common interfaces. Then we have admission experts. As mentioned earlier, an admission is usually required, which makes independent experts who inspect the autonomous system necessary. Next, there are stewards or safety drivers. To this date, safety drivers are still required by law during operation. But even if true Level 5 autonomous driving is here, stewards may still be present for convenience, for example in an autonomous bus. And finally, there are operators that want to monitor and supervise their fleet from a remote control center. The software development is characterized by the component-based design approach, as mentioned earlier. Although this supports development in large teams, challenges arise. Components may be updated and changed individually, which makes tracking of the software version necessary. Additional effort is required. Although interface definitions are used to ensure interactions of components, these interfaces must be accurate and complete and have to cover all possibilities. And also in an autonomous driving system, the dependencies between components may be complex and not easy to understand. Two completely separate components with no distinct connections may depend on each other, and failures in one component may influence the other. Also, development and testing needs to consider the whole system and cannot be restricted to the individual components. And the collaboration is usually focused on the driving task and not on failures and malfunctions of the components' interaction. Of course, autonomous driving needs to be safe. Injuries or even death to passengers or traffic participants must be ruled out in all cases. This holds for early autonomous driving as well as modern-day autonomous vehicles. What's new are the consequences of failures. Modern autonomous vehicles are often operated by large companies. In case of accidents with injured people, these companies risk a bad reputation, as we have seen in the past. But even if the vehicle operates safe, a bad reputation might follow if the vehicle shows annoying behavior, like for example reduced speed because of malfunctioning components or too frequent stopping maneuvers. Thus, a failure-free operation is crucial and periods with limited functionality have to be minimized. Another challenge are the new use cases. In modern-day applications, several tasks have to be carried out that are not part of the classic driving task. For example, in a door-to-door, on-demand transportation scenario, the vehicle not only has to drive, but for picking up passengers, it may also stop at almost everywhere. No distinct bus stops might be present, which makes it necessary that the vehicle searches for suitable stopping points itself. Also, the route is not fixed from the beginning to the end, as new destination points might make route adaptations necessary. Cities may even oblige autonomous driving operators to connect to the provided intelligent infrastructure for traceability reasons. All of this makes the autonomous driving software even more complex and more prone to errors. Insights to the fitness of the system is therefore tremendously important, as errors in component interaction during complex edge cases might not be recognized during development. With the mentioned challenges of multiple actors that require a common interface to the autonomous driving system, the heterogeneous software design which makes testing of the complete system with all of the interactions necessary, the increased complexity due to new use cases, and of course the importance of safety and reliability, a solution to gain insights to the healthiness of the complete system and its subparts needs to be found. Such a solution might be a diagnostic system that gathers status information of the system and its various parts and automatically generates the needed insights, which can then be utilized by the various actors or can support automatic preparation techniques. Thus, in the following, we will provide a concept for diagnostics in autonomous driving, which helps to tackle the mentioned challenges. We define diagnostics in autonomous driving as follows. Diagnostics in autonomous driving is the task of independently inspecting an heterogeneous component-based software system by analyzing component self-states and indirectly observing their behavior to gather additional information not related to the driving task for supporting system metaparameters improvement like robustness and availability and/or reparation techniques. For our diagnostic system to be able to judge the state of the system and its parts, we rely on status messages. Status messages indicate the healthiness of a distinct entity, which might be a component, a subpart, or a function of the system. We consider the following characteristics of status messages. On one hand, a status message might directly indicate the healthiness of an entity, or on the other hand, to be able to judge the healthiness, the status must be processed or transformed. This can be, for example, a simple threshold. If a status message is not received, this does not necessarily imply a failure. An entity might be busy with other tasks, or the network over which the messages are delivered is busy. Diagnostic information may also advance. Messages from new entities and new message types may be received, and other ones may disappear. This dynamic behavior needs to be considered. The diagnostic system should not be programmed to receive specific status messages, but rather learn which states are important. Different state spaces must also be considered. To be versatile, status messages should have a generic type. State spaces can be discrete or continuous, and even complex data might be considered as a status, like, for example, temperature, CPU load, and so on. Also, additional attributes are required for further processing, such as an ID of the status message, a timestamp, or its origin entity. Status information can be obtained in different ways. On one hand, entities might directly report status messages. This is shown in the image, where component A directly sends status messages to the overall diagnostic system. If an entity is not reporting its status, the state can also be observed. In the image, this is shown on the right side, where the overall diagnostics entity observes the behavior of component B and also observes the communication path M. Here we provide a concept of a diagnostics architecture that allows to tackle the previously mentioned challenges. The goal of this architecture is to process the available status messages, to provide insights to the system and its entities for usage by other components that deal with the occurring failures. These components can be, for example, automatic repair mechanisms or simply by informing the remote operator. First, the architecture analyzes incoming status messages. This is needed because the messages have different state spaces and might also be unreliable. Next, dependencies between these status messages are inferred. In the autonomous system, a failure in a single component usually propagates to other components. Cascading failure effects are the result. These effects are also reflected in the status messages, making them highly dependent on each other. Furthermore, not all states may be seen by the diagnostic system, so that in this stage, hidden states are also determined. With all the generated information, the next stage predicts future state changes. This helps, for example, repair mechanisms to intervene before the severity of a failure increases. Also, a single status message is usually not useful on its own. Depending on the use case and the user, the system also provides aggregated information on the important parts of the system. And finally, the whole concept is driven by self-adapting models that adapt during runtime and make it possible for the system to dynamically adapt its behavior. The generated information of the diagnostic system can then be used to increase safety, reliability, and robustness of the autonomous vehicle. Of course, a human operator can use the information in case of a failure to assist or intervene. Automatic repair mechanisms are another example for an entity that utilizes the results of the diagnostic system. Note that the repair mechanism itself is not part of the diagnostic system. As previously mentioned, a single component's failure might affect other components due to complex dependencies. In such a case, an automatic repair mechanism might activate other components that are able to fulfill the missing tasks to a certain amount. With this, we come to the conclusion, where we summarize the results and present open research questions. We first motivated the need for a diagnostic system with simple examples in the scope of autonomous driving. We then showed that modern-day autonomous driving has its distinct challenges, which make an independent overall system that provides insights to the healthiness of the autonomous driving system necessary. As a solution to these challenges, we claimed that a diagnostic system provides the needed insights. After defining diagnostics in autonomous driving, we provide a concept of a learning-based diagnostic system together with examples of how the generated information might be used. Open research questions are: which diagnostic information needs to be derived so that the overall safety, robustness, and reliability of the vehicle can be increased? Can atomic units and thus possibilities for redundancies of the system be identified? And which exact aspects of the diagnostic system need to be learned to provide the most flexibility? We will address these questions in future research based on this article. The research leading to the presented results was conducted within the project Smart Load, which is funded by the German Federal Ministry of Education and Research. Thank you very much for your attention.